Dr. Anthony Raj. He has pursued his bachelor's, master's and MPhil in physics. He then went on to pursue his PhD in physics at the University of Madras as well. He then went on to work as a lecturer at Thiruvalluvar Arts and Science College and Idya Engineering College for Women. Since the year 2006, he works as the lecturer and assistant professor at Loyola College, Chennai. With regard to research, he has published several papers in international journals, namely Radio Wave Propagation over Salem, Linear and Non-Linear Optical Properties of Pure and Doped Selenium Malate Single Crystals, and many more. He has also attended several conferences and seminars, namely International Conference on Materials Science and Technology, National Conference on Higher Education at Crossroads held at Loyola College, National Seminar on Crystal Growth 12 held at VIT University, and many more.
Welcome to UGC lecture series BSc Physics Honors Mathematical Physics 2 Semester 2 Lecture 10. In this lecture, we are going to see equations reducible to linear differential equations with constant coefficient. Here, this Cauchy-Euler homogeneous linear differential equation can be reduced to linear differential equation with constant coefficients, and legendary homogeneous linear differential equation can also be reduced to linear differential equations with constant coefficients. Cauchy-Euler homogeneous linear differential equations. A linear differential equation of the form a0 x power n d power n y by dx power n plus a n into x power n minus 1 into d m power n minus 1 y by dx power n minus 1 plus a2 x power n minus 2 into d n minus 2 into y by dx n minus 2 plus etc. plus a n y is equal to f of x is a linear equation. Here in this linear equation, this a1, in these linear equations constants a1, a2, an are constants, and f is either a function of x or a constant. This equation is called Cauchy-Euler homogeneous linear differential equation. Now, what we are going to do is we are going to reduce this homogeneous linear this Cauchy-Euler homogeneous linear differential equation with constant coefficients. To do so, what we need to do is we are going to substitute some variable, and that is reduced further. We will get the required linear homogeneous equation with constant coefficient. In that Cauchy-Euler equation, the index of x and order of derivative is same in each term of such equation. That is the thing about this Cauchy-Euler homogeneous linear differential equation. Now, in that equation, what we are going to do is we are going to use the d symbol. The d symbol is used instead of the differentiation, where first d is equal to d by dx and d square is equal to d square by dx square, that is double derivative of a function with respect to x is considered as d square, is symbolically represented as d square. In similar manner, if you extend to all powers of d, finally we will get d power n, that is derivative of a function to n times with respect to x, that is denoted as d power n by dx power n. If we use these symbols, that Cauchy-Euler equation will reduce to a form a0 x power n d power n plus a1 x power n minus 1 into d power n minus 1. The d power n minus 1 says that derivative of a function with respect to x n minus 1 times, That is the meaning of this d power n minus 1. Here in this component of this equation, you can see the order of x, order of derivative and the power of x will be same. Then the next component in that equation will become a2 into x power n minus 2 into d power n minus 2 plus etc. plus an into y is equal to f of x. This is how that Cauchy-Euler linear differential equation will reduce after using the symbols d, d square, d power n. The above equation can be reduced to linear differential equation with constant coefficient by some substitution. What we are going to substitute is x is equal to e power z is a thing we are going to substitute. If x is equal to e power z, then natural logarithm of x is equal to z. Here dz by dx will become 1 by x. This is what we are going to substitute to reduce this equation to the form of linear differential equation with constant coefficient. Then using the chain rule in the differentiation, we will get dy by dx is equal to dy by dz into dz by dx, which is equal to 1 by x dy by dz, because this dz by dx is equal to 1 by x and this dy by dz exists as it is. So, this is the value of dy by dx after using the chain rule. So, dy by dx is equal to 1 by x dy by dz. Now, we need to define a new operator. What is that new operator is? D by dz is equal to d1. Earlier we used an operator d which is equal to d by dx. Now, d by dz, because we are substituting x is equal to e power z, so that this d by dz should be assumed. So, this operator d1 is equal to d by dz. Then we have x dy by dx is equal to dy by dz, x dy by dx is equal to dy by dz, which is equal to x dy, which is equal to d1 y. Because this d1 is equal to d by dz, then this x is as it is, then d by dx is taken as d, then y exists as it is, then d by dz is d1, then y exists as it is. This is how this x dy by dx will reduce after substituting the operator. Similarly, for the second order derivative, this d square y by dx square is equal to d by dx of dy by dx. So, this d square y by dx square is equal to d by dx of dy by dx, that is this d by dx is differentiated again with respect to x, that is what this quantity says, which is equal to d by dx, that is differentiation with respect to x into the value of dy by dx. The value of dy by dx is 1 by x into dy by dz, which is equal to, again we need to differentiate this using UV rule. If we use UV rule, we will get minus 1 by x square into dy by dz plus 1 by x d by dx of dy by dz. This is what we will get after using the UV rule, which is equal to minus 1 by x square dy by dz plus 1 by x. This d by dx of dy by dz can be written like this: d by dz of dy by dz into dz by dx. So, this is how this d by dx of dy by dz can be written, which is equal to minus 1 by x square dy by dz plus 1 by x square d square y by dz square. This is the expression for d square y by dx square. So, we got the double derivative of y with respect to x. The double derivative of y with respect to x is equal to minus 1 by x square into dy by dz plus 1 by x square into d square y by dz square. Thus, we have x square into d square y by dx square is equal to d square y by dz square minus dy by dz. So, here you can take this 1 by x square as common. So, this equation will reduce to 1 by x square into minus dy by dz plus d square y by dz square, which is equal to d square y by dx square. Now, bring this x square which is in the denominator to this side, you will get x square into d square y by dx square. That is what exists here. X square into d square y by dx square is equal to the remaining component d square y by dz square minus dy by dz. Now, substituting the operators assumed, this equation will reduce to a simplified form as x square into d square, because this d square by dx square can be written as d square into y is equal to, this is d1 into d1 minus 1 into y, where here you can write d1 square, because here the differentiation is with respect to z. So, d1 square into y minus d1 into y. Here one d1 is taken common. So, that expression will reduce to d1 into d1 minus 1 into y. Similarly, we can write for x cube d cube y, which is equal to d1 into d1 minus 1 into d1 minus 2 into y, and so on. So on, in the sense x power 4 d power 4 y is equal to d1 into d1 minus 1 into d1 minus 2 into d1 minus 3 into y. So, this is how you can keep on write the given thing in operator form. In general, we get a relation x power n d power n is equal to x power n d power n is equal to d1 into d1 minus 1 into d1 minus 2, then d1 minus 3, d1 minus 4, etc. it goes, and we got d1 minus n plus 1 into y. So, this is the final expression we get for x power n into d power n. Substituting the values of x, x d, comma x square d square, etc., and x n dn in equation 1, we get a naught d1 into d1 minus 1, that is x n, then etc. d1 minus n plus 1 plus etc. plus a n minus 2, a suffix n minus 2 into d1 into d1 minus 1 plus a suffix n minus 1 into d1 plus a n into y is equal to f of e power z. This is how we will get the equation after substituting the values of x, x power x d, x square d square, etc., x power n d power n in equation 1. This equation is the linear differential equation with constant coefficient. With constant coefficient. This equation can be solved by various methods applicable to solving the linear differential equation. This is how we can reduce the Euler equation to a linear differential equation with constant coefficient. Now, we will understand this reduction of Euler equation to linear differential equation with constant coefficient by some example. Example 1. Solve the differential equation x square d square plus x d minus 4 into y is equal to 0. So, this equation can be solved by adapting the method which we learnt in earlier theory. In earlier theory, first what we did is we substituted an exponential function. That exponential function is substituted for x, where it is assumed that x is equal to e power z. Then we removed that exponential function by taking logarithm. So, we got log x, that is natural logarithm of x is equal to z. Then we differentiated that z with respect to x. Like that we proceeded with some steps. We can apply the same steps here to solve this differential equation. So, solution to this differential equation can be obtained by the method of substitution. First, what we need to do is we need to reduce this differential equation to the form of linear differential equation with constant coefficient. To do that, we are doing this substitution. X is equal to e power z, which is equal to ln of x is equal to z. Then we know x d is equal to d1. Similarly, x square d square is equal to d1 into d1 minus 1. All these things we derived in the earlier theory. We are using those concepts here. Then the given equation, by substituting these values, the given equation will reduce to d1 into d1 minus 1 plus d1 minus 4 into y, because here x square d square is nothing but d1 into d1 minus 1, that is substituted here, plus xd is nothing but d1, that is substituted here, minus 4, that is substituted here, which is equal to 0. Now, If you simplify this, that equation will reduce to d1 square minus 4 into y is equal to 0. This is how that equation will reduce. Now, we can use that characteristic equation method to solve this differential equation. So, the characteristic equation is m square minus 4 is equal to 0. So, roots of this characteristic equation will be m is equal to 2 comma minus 2. So, the required solution of the transformed equation in the sense equation which is transformed to the form of linear differential equation with constant coefficient. The solution of that transformed equation will be like this: y is equal to c1 e power 2z plus c2 e power minus 2z. This is how the solution of the transformed equation. Here in this solution z appears. We need to change this z to x. So, resubstitute the substitution we made at the starting of this problem. What substitution we made is log x is equal to z. So, substituting log x is equal to z, the desired solution here instead of z substitute log x. So, it will reduce to x square. This e power 2 log x will reduce to x square. So, the solution will become y is equal to c1 x square plus c2 x power minus 2, where c1 and c2 are arbitrary constants. This is how you can obtain the solution of a differential equation and of a differential equation in the form of Euler equation. We can reduce the differential equation to a linear differential equation with constant coefficient and solve that and resubstitute the substitution we made at the starting of the problem. We will get the solution in the form of x. Now, we will do one more problem to understand this reduction of linear differential equation with constant coefficient. Here the problem is find the general solution of the differential equation x square d square plus y into y is equal to 3x square. In the earlier example, we got a homogeneous linear differential equation, that is right hand side of the equation is equal to 0. But here you got a non-homogeneous differential equation. This non-homogeneous differential equation consists of two parts in the solution, that is complementary function and particular integral. So, first find the complementary function and then find the particular integral, then sum that two, you will get the general solution of this differential equation. But the procedure to solve is same as we used in the earlier problem. So, first what we need to do is we need to substitute x is equal to e power z. Then the given equation reduces to d1 into d1 minus 1 plus 1 into y is equal to 3 e power 2 z. This is how the given equation will reduce, because we know that x d is equal to d1, then x square d square is equal to d1 into d1 minus 1. This is what we learnt in the theory of reduction of linear differential equation with constant coefficient. We just substituting these operators in the given equation. Here in the given equation is x square d square. X square d square is d1 into d1 minus 1. So, d1 into d1 minus 1 plus y plus y. So, plus y is equal to 3 x is 3 x square. Instead of that x, e power z is substituted. So, we got e power 2z. Now, simplify this, we will get d1 square minus d1 plus 1 into y is equal to 3 e power 2z. This is how that equation will reduce to the form of linear differential equations with constant coefficient. Now, bring the characteristic equation of this differential equation. The characteristic equation of this differential equation will be m square minus m plus 1 is equal to 0 is the characteristic equation of the above differential equation. Now, solution of this characteristic equation will be m is equal to 1 plus or minus I root 3 by 2. This is the roots of this characteristic equation. Therefore, the complementary function for this differential equation will be, the complementary function is equal to e power z by 2 into c1 cos z root 3 by 2 cos z root 3 by 2 plus c1 sin z root 3 by 2, sin z root 3 by 2. This is the complementary function of the given differential equation. Now, substituting z is equal to ln of x in this complementary function, we get complementary function is equal to root x into c1 cos ln of x root 3 by 2 plus c1 sin ln of x, that is natural logarithm of x root 3 by 2 is the complementary function after substituting z is equal to ln x. So, one part of the solution for that non-homogeneous differential equation is obtained. The next part is particular integral. To get the particular integral, we have to adapt any of the method we know. So, here the easiest method to obtain the particular integral is equal to 1 by d1 square minus d1 plus 1 into 3 e power 2z. This is the method to get the particular integral of the above differential equation. Now, which is equal to 1 by 2 square minus 2 plus 1 into 3 e power 2z, which is equal to e power 2z, because here 4 minus 2, which will give 2 plus 1 3. So, 1 by 3 into 3 gets cancels, we get e power 2z. So, the particular integral is e power 2z. Hence, the desired solution for the above differential equation will be y is equal to root x into c1 cos ln of x into root 3 by 2 plus c1 sin ln of x root 3 by 2 plus e power 2z, where after substituting z is equal to that ln of x, we will get x square. So, that is the complementary function for this particular integral for this differential equation. So, this is the final solution of the differential equation. So, in this method, in this example, we learnt how to get the solution of a non-homogeneous differential equation which is reducible to linear differential equation with constant coefficients. Summary: after listening to this lecture, we know how to reduce the Cauchy-Euler homogeneous linear differential equation to a linear differential equation with constant coefficients, and how to obtain the solution of a linear differential equation with constant coefficient. Then Legendre's homogeneous linear differential equation can be reduced to constant coefficient linear differential equation by substituting x is equal to e power z. Solution of this homogeneous linear differential equation consists of complementary function and particular integral. So complementary function, obtaining complementary function can be done by any of the method easy to us, and obtaining particular integral of a non-homogeneous linear differential equation can also be done by any of the method we know. So these are all the concepts we learnt from this lecture. After listening to this lecture, we can solve these questions. Solve x cube d cube plus 3x square d square minus 2xd plus 2 into y is equal to 0. Then write Legendre's homogeneous linear differential equation. Solve x cube y double prime plus x y prime minus y is equal to 3x power 4. You can answer these questions after listening to this lecture. Thank you.